All right, welcome everyone. Today we're going to look at trigonometric integrals, and specifically we're going to start looking at how to integrate functions involving powers of sine and cosine. All right, so in this lesson we're going to see how to calculate integrals of this form. Sine of x raised to the power m times cosine of x raised to the power n. And for the most part, we're going to be looking at cases where m and n are non-negative integers. So for the most part, they're going to be positive, or maybe one of those exponents is going to be 0. So, like a sine term or a cosine term doesn't show up. But for the most part, we're going to be looking at these cases where the exponents are either both positive or maybe one of them is 0. But a lot of the techniques and strategies that we're going to see can be used when m and n maybe are negative. Maybe one of them's negative, or maybe we have fractional exponents. So a lot of the techniques and strategies that we're going to see here can be kind of extended beyond these cases. All right, but for the most part, today we're going to be looking at integrals of the form sine of x raised to the power m, cosine of x raised to the power m, and we're going to see these as being non-negative integers. Those are the examples we're going to look at. Now, there's going to be two real cases we're going to have to consider, two different strategies. So the one we're going to look at today is where at least one of these exponents is odd. So we have an odd power. And at least one. Maybe both of them have an odd exponent. But if we have at least one of those as being an odd exponent, we're in good shape and we'll be able to use the strategy we're going to look at today. The other scenario is if both of those exponents, both of those powers are even. So if both of them have even exponents, even powers, then we're going to have to use a different strategy, and we'll look at that next time. All right, so what is our strategy going to be? Well, for odd powers, it's all going to kind of hinge around one of our standard trigonometric identities, and that's sine squared plus cosine squared is equal to 1. So formally here we have it written as sine squared of theta plus cosine squared of theta is equal to 1. And we're going to use this in a lot of our examples here. All right, so what is the strategy? So if we look at our integral and one or maybe both of our sine and cosine terms has an odd power, then the first step is to really identify which trig term is our odd power. And so if we see, and once we do that, then we factor off one trig term from that odd power and we put it next to the dx. So we're going to kind of split up whichever term has an odd power, and we're going to kind of peel off one of the trig terms and move it next to the dx. And we'll see how that works in the first example. Then we're going to have a whole bunch of trig terms left over. So step 2 then is to convert all of those remaining terms into the opposite trig function. So what do we mean by opposite trig function? Well, it's whichever trig function we didn't identify in step 1. So, if we identified cosine as being our odd power, well, then we would say sine is the opposite trig function. So in step 2, we're going to convert all remaining trig terms that we see to our opposite trig function. And the way we're going to do that is with this trig identity. So in step 2, this is where we use that trig identity. And then steps 3 and 4, we're going to do a u substitution. So we're going to let u equal our opposite trig function. So whichever one we didn't identify in step 1 there. And then we'll go through a usual substitution rule. So we're going to let u equal whatever our opposite trig function is. So if we said cosine had the odd power that we worked with in step 1, well then we're going to set u equal to the opposite trig function. We're going to set u equal to sine in that case. Let's see how it works. So let's look at example 1. We have the integral of cosine cubed, cosine of x cubed. And when we look at this, the odd power term, give a little more room, the odd power term here is cosine. And so what we want to do in step 1 is we want to separate off, we want to factor off one of those cosine pieces, and we're going to split it up. So that's step 1. We're going to take our odd power, and we're going to peel off one copy of that trig function, and we're going to move it next to the dx. So our odd power was cosine cubed. We're going to take one of those cosine terms, break it off, and put it next to the dx. That's step 1. Step 2 is we have these cosine squared terms, and we're going to convert those into our opposite trig function. So we're going to convert all of these into sine of x's. And we're not going to do anything with that one cosine term that we peeled off, and we're not going to do anything with the differential right now. So all we're going to do is we're going to look at everything else that's left in our integral, in this case the cosine squared, and we're going to convert that in some way to sine terms. And how are we going to do that? Well, we're going to use our trig identity. So we know sine squared of x plus cosine squared of x is equal to 1. So we can just solve this trig identity for cosine squared. So cosine squared of x is equal to 1 minus sine squared of x. And that's what we're going to plug in here. So we're going to have the integral of 1 minus sine squared of x times cosine of x dx. So step 1, we identified the odd power, and we peeled off one copy of that trig function and put it next to the dx there. Step 2, we use our trig identity to convert all of the remaining cosine terms into sine terms. So now we've converted all of that into an expression involving only sine. Step 3, we're going to do a u substitution, and we're going to set u equal to sine of x. So we're thinking of, in this case, we're thinking of sort of the opposite trig function as sine of x. So our odd power was cosine, and then what's the opposite trig function from cosine? We're going to think of that as being sine of x. So our odd power was cosine here. We peeled one copy off. We converted everything, all of the other cosine terms into sine terms, our opposite trig function, and then we're going to let u equal that opposite trig function. We're going to let u equal that sine of x. And why are we going to do that? Well, when we calculate du, the derivative of sine of x is cosine of x. And now we're going through our usual substitution rule steps. So we calculate du, we get the derivative as being cosine of x, and then we multiply by dx. And if we compare here, we're going to put everything in. We're doing a substitution, so we're going to put all of this into our integral. And kind of by design, we can see why we separated off that one cosine term. And that's because we now have a very nice match here with our differentials. So we're going to be able to do this substitution rule, and almost by design, things are going to match up very nicely. So when we look at this, I know the sine squared here is going to become u squared. And I know the cosine x dx here is going to become my differential, my new differential du. So that's step 3, is to really just start the substitution, the u substitution. So if we put all of our ingredients in, we get 1 minus u squared times du. And now we just finish that integration. So now we just go through like it's a usual substitution rule. So we do the antiderivative. We get u minus 1/3 u cubed plus c. And then we're done. We found the antiderivative. The only thing left to do now is to convert back to the original variable. And so that's really our last step, is to just finish the integration. So when we convert back, the u term here, that's going to become just a sine of x. Then I have my minus 1/3. And then instead of u cubed, it's going to be sine cubed. And then we have our plus c. And there we go. We found our antiderivative. So that's really our strategy. Identify the function that has the odd power, peel off one of those trig functions there and put it next to the dx, convert everything else to the opposite trig function. So we converted all of our other cosine terms into sine terms using our trig identity. And then also we set up our u substitution. So we let u equal our opposite trig function. So we let u equal our sine of x. We started our substitution rule. We put everything in just like we normally would, and then we finished the integration. Let's try another one. Look at example 2. So here we're going to integrate the function sine of x times cosine of x. And when we look at this, both the sine and the cosine term have an odd power. They both have an odd power of 1. So it really doesn't matter which one we, we kind of have two options for how we're going to handle this. We could kind of separate off one of the cosine terms, or if we wanted to, we could separate off one of the sine terms. And you'll get slightly different looking answers, but they would be equivalent. So let's say our odd power, I did it again. Let's say our odd power is cosine. Same as what we did in example 1. So what are we going to do? Well, we're just going to, it's not going to look like we do much here, but this is more of like what we're thinking in our head. So we're going to separate off. We look at our cosine term. There's only one copy of cosine there, so there's really nothing to factor off. We're just going to think of it as being right next there to our dx. So maybe put a little space in there, a little multiplication sign, just to really emphasize that we've factored that cosine term and we've moved it next to the dx. So then normally we look at everything else in our integral here, and we would want to convert anything that's left over, we would want to convert it all to our opposite trig function. So we'd want to convert everything here to sine. All right, so step one is to identify the odd power that we're going to use. So we're using cosine as our odd power. So we move one lone cosine term next to our dx. And then in step two, we look at everything else that's there, and we convert it all into sine terms. Now, this is already done for us. All we have there is a sine term. So there's really not much we need to do here. But if there were other terms here, other cosine terms, we would have to use our trig identity to kind of get rid of them and convert them into sine terms. So step two is already basically done for us. And, well, all right, it's not looking like we're doing much here. So we're going through our steps. And I probably shouldn't have rewrote that, but what are you going to do? So step three then is to identify our u substitution that we're going to use. So we said cosine was our odd power. So we're going to think of our opposite trig function as being sine. Sine of x. So that's what we're going to use for u. We're going to let u equal sine of x. So we kind of, for these problems, you want to kind of think of sine and cosine as being sort of opposite each other. So step one, we identify the odd power. We move one factor of that odd trig function next to our dx. In step two, in this one, there's really not too much to do, but we would look at all of these remaining terms and we would convert them to our opposite trig function. So we'd want to convert everything here to sine. It's already been done for us, basically. Then in step three, we start our u substitution. So we let u equal our opposite trig function. So we're going to let u equal sine. We calculate du. We get cosine of x dx. Derivative of sine is cosine. And when we look at this, cosine x dx, well, that matches up nicely with our differential du for our substitution rule. And then the sine of x right here matches up nicely with what we picked for u. So this is just going to become u. So when we put everything into our integral, it's just going to be the integral of u du. And that's not too bad. So what's the antiderivative of u? Well, it's 1/2 u squared plus c. And then the last step, step four, convert back to x. So we get 1/2 sine squared of x plus c. And there we go. All right, so that one was a little, it was probably one of those examples where if you're looking at it, it might be almost too easy. So that's why I wanted to do it, is because, you know, this one is going to show up a little bit. So it's good to see this one at least once and to see how this strategy applies. But let's try one now where there's going to be a little bit more kind of algebraic work involved. All right, so now let's throw in some big exponents. We have this function sine of x raised to the power 5 times cosine of x squared. And what we're going to do in step one is we want to identify the odd power. So our odd power here is sine of x. So what we're going to do is we're going to look at that sine of x raised to the power 5. There's 5 copies of sine right here. We're going to take one of them and we're going to move it next to the dx. So we get sine raised to the power 4x times cosine squared raised to the power, or cosine squared of x times sine of x. dx. So we've basically taken one of these copies of sine here. There's 5 of them, so we take one of them, move it next to the dx, and that leaves us with 4 left. So we have sine of x raised to the power 4 times cosine of x squared times sine of x. All right, so what we want to do then is we look at everything else that's left in our integral here, besides that sine of x that we kind of separated off. We look at everything else, and we want to convert all of this into our opposite trig function. All right, so we said sine was our odd power, so our opposite trig function then is going to be cosine of x. So we want to convert everything right here, the sine of x raised to the power 4, the cosine of x squared, we want to convert all of that into cosine terms. We're not going to do anything with that sine of x because we know we're saving that for when we do our substitution rule. But everything else there, we got to get into cosines. And again, the trig identity we want to keep in mind is sine squared of x plus cosine squared of x is equal to 1. And so in order to help us with this, we want to get this even power of sine here, we want to somehow get it in the form of sine squared. And if we can do that, we can solve this equation for sine squared. And we know sine squared then is equal to 1 minus cosine squared. All right, so how are we going to do that? We want to essentially get a bunch of sine squareds here. Well, we started with an odd power. So we took one of those sine terms and move it next to the differential. That means all of our sine terms here it's an even power. So we can just break it up into as many sine squareds as we need. And that's what we're going to do. We're going to break that into sine squared of x times sine squared of x. And then we have our cosine squared of x. And then we still have our sine x dx. So this sine of x raised to the power 4, we break that into as many sine squared terms as we need to, as there are. So there's 4 copies of sine, and then we break them into a sine squared and a sine squared. All right, so once we do that, then we can take that result from our trig identity and we can just plug it in as many times as we need to. So we know sine squared is 1 minus cosine squared. We know this sine squared is 1 minus cosine squared. If there was more, we would just keep going. So in this case, we only need to do those 2. So let's see what we would get. We get the integral of 1 minus cosine squared times 1 minus cosine squared times cosine squared times sine of x dx. All right, so now we're ready for our u substitution. We've gotten rid of, excluding that differential there, everything else here is now in terms of cosine. So we're in good shape. So we're ready for our u substitution. So we're going to let u equal our opposite trig function. So we're going to let u equal cosine. And that's going to allow us to get rid of all these cosines that we see here. We calculate the derivative. We're going to calculate the differential du. So the derivative of cosine is negative sine. And then we put on our dx. Now if we compare this with what we actually have in the integral in the integral we have sine of x dx. Here we have this extra negative. So we do need to do a little bit of work to make this match exactly. But that's just an extra constant, so that's no big deal. So we can move that negative to the other side. And I'm probably going to need a little bit more room. So let's... So we're just going to take that negative, divide both sides by it. That gives us a negative on the left. So we get negative du is equal to sine of x dx. And that's what we're going to be able to fill in right here. So let's go through now and plug all of these pieces for our substitution in. So when we look at this, we know this cosine squared is going to become a u squared. We know this cosine squared is going to become u squared. And we know this cosine squared is going to become u squared. And then this term at the end, the sine of x dx, we know what that is. That's going to become negative 1 times du. So let's fill all of our pieces in. So we're going to have the integral of 1 minus u squared times 1 minus u squared times u squared times negative 1 du. And we're at a point now where we can just multiply all of this out. So just multiply all of this out. And if we do that, it's going to take a little bit of work. But if we do that, we can then use power rule to just do the integration. So let's start by multiplying out the 1 minus u squared with the 1 minus u squared here. So we get the integral of 1 minus 2u squared plus u to the 4th. And then we have negative u squared there, du. So we've multiplied out in that step, we've multiplied this out. Now in the next step, and we've also multiplied the negative 1 with the u squared. Now let's take that negative u squared and distribute it inside the parentheses there. And so when we do that, we get, what do we get? The integral of negative u squared plus, so we end up with a double negative, so it becomes positive, plus 2 u to the 4th minus u to the 6th du. And now when we look at this, power function, power function, power function. So what does that mean? Power rule, power rule, power rule. And that's always a good thing. So now we actually find the antiderivative. So what's the antiderivative of u squared? Well, it's negative 1/3 u cubed. And we had the negative in front. What's the antiderivative of this 2u to the 4th? Well, it's plus 2 over 5 u to the 5th. And then what's the antiderivative of that u to the 6th term? Well, it's 1 over 7 u to the 7, and we had a minus in front. And then our usual plus c at the end. And this is looking pretty good. We have our antiderivative now. So we're done with the actual integration. The only thing that's left to do, as is usual for substitution rule, is to convert all of these u's back to our original variable x. So what was our original variable here? Well, we need to convert back with this cosine term. So wherever we see a u here, see one here, here, and here, we're going to replace that with cosine of x. So let's do it. We get negative 1/3 cosine cubed of x plus 2 over 5 cosine to the power 5 of x minus 1 over 7 times cosine to the 7 of x plus c. And there we go. We're done. We have our antiderivative. And it's all in terms of our original variable x. So this is kind of a more extreme example of of what we need to do. So let's just kind of go through the steps one more time. What did we do? First step, we identified which piece had the odd power, so that was sine. So we took one of those signs, put it next to the dx. Step 2, we looked at everything that's left in our integral besides that one sine term that we peeled off, and we converted everything that we saw there into cosine terms. And the way we did that is we looked at the sine to the fourth, we split it up into a bunch of sine squareds, and then we used our trig identity to say sine squared is actually equal to 1 minus cosine squared. So we ended up with 1 minus cosine squared times 1 minus cosine squared times cosine squared times our sine x dx. And then from there we did a u substitution where we let u equal our opposite trig function. So our opposite trig function was cosine. So we're letting u equal cosine, and then we went through our usual substitution rule. So this is the technique we're going to use when we have an odd power of sine or cosine, or as we saw in example 2, maybe have both of them have an odd power, in which case, you have some options there. So we could have done example 2 slightly different. We would have ended up with a kind of a different looking answer, but it would have been equivalent. So as long as at least one of those powers is odd, we can use this strategy. Next time we're going to see what happens if both of the powers, both of the exponents, are even. So it's going to be a slightly different strategy for that. All right, so that'll do it for today. And like we said, tomorrow we're going to see what happens with even exponents. More trig identities, I guess. We'll see it then. All right, we'll see you later. Bye-bye.